Okay, so let's continue with what we saw yesterday. So here's the proposition I announced last time. So we take a smooth and projective variety over field K, and there are three properties. So the first one is if the base field is a field of complex numbers. Then if you have a trivial group of 0 cycles of degree 0, then it's a result by Bloch and Srinivas that algebraic and homological equivalences coincide for codimension 2 cycles. Also, one has Hodge conjecture for cycles of codimension 2. So this I put it mostly for general culture and for the history of these properties. What we will be interested in, it's mostly the second property and the third one. So the second one is, for field of complex numbers. If we assume that X has a universally trivial CH0 group, then we have no torsion in the Betti cohomology H3 with integral coefficients. And finally, if again X is universally CH0 trivial, then no global sections for differential forms for any I positive. And this actually holds for any K. We don't even need to assume K equals to K bar here. Okay, so let me show you how one can prove the second property. Okay, so proof of 2. So we have this condition, and by the lemma, which I called lemma 1 last time, it gives you that X has an integral Chow decomposition of the diagonal. So we write the diagonal in X in this way. It is sum of 2 cycles X cross little x plus Z, where plus 3. Where little x is the point in X, and Z supported on D cross X. Okay, D codimension at least 1. So sometimes it is useful to look at this decomposition of diagonal, and sometimes it could be useful to use the transposition of 2 coordinates in X cross X, and to use the transposed decomposition. So it is actually what we will do in this case. So by transposing, what we get is the same diagonal because, well, it doesn't change. And then we have little x cross x plus, I will call Z1, where Z1 supported on X cross D. So it actually works better here. Okay, so now recall that we can view this diagonal as a map. So it gives a map from, in particular, the third cohomology here. And that for diagonal, it is identity. Now we have these compositions. Sorry. We have this decomposition, so we can look at 2 maps induced by this cycle and this one. Okay? And so now we can view X cross X inside X cross X, okay, but also inside X little x, inducing the maps between cohomology of just the point and X. And also, so the same thing for Z1, so let me do some notations. So put D tilde to D, a resolution of singularities, V over C of singularities. Of D. Okay, And so we may assume it will be just more convenient. We may assume that d tilde is irreducible. Yeah, well, you may complain, but just by arguing component by component. Okay. So if you don't like this, just do this for all component of d tilde by component. And also we, oops, well, and also let me denote P a map from x cross d tilde to x cross d. And we may assume as well that Z1 is obtained by pullback from some cycle Z1 tilde for Z1 tilde in x cross d tilde. So this is it for notation. Let me just put again n equals to dimension of x. And toward the inclusion of, no, it's not an inclusion, it's a composition of d tilde to d and the inclusion. Okay. So these are all preliminaries just to develop the action of correspondences for this Z1. So let's recall from what we saw last time how these maps are actually defined. Okay. So probably I will write it here. So how does it work? So we take, we want to understand this map. Okay? And this goes from H3 x z, and it ends here as well. Okay, so by definition, we have here, first we have to take their pullback by the first projection. And like this, we arrive to H3 of the product with its coefficients, right? I'm just writing the definition of this map. Then, because it is Z1, so we take an intersection with the class of Z1. So I put times class of Z1. So probably I ask you what degree we obtain. I hope I didn't make a mistake, so I obtain this one. Okay. And then I take a push forward by the second projection. So here is just, I just recall the way we define this correspondence. Okay? And now remember that this Z1 actually lives inside here. Okay? So this Z1 living inside x cross d tilde allows us also define maps between cohomology of x and the cohomology of d tilde. So I will write it there just down on the line, which will be just down this one. Okay, so we start with x, right? And this time we arrive somewhere to d tilde. I will put here the index here later. So I just want to say that it's important that x is smooth here, just in order to be able to define these intersection products. So that's why, in particular, we introduced this resolution of singularities of d. Okay. So we write actually the same thing. So just for d. So again, the first projection. And this time I arrive to x cross d tilde z. And now I have a product with class of z1 tilde. And this time we arrive to h2n, oops, okay, so it's not, sorry, 2n plus 1. Yeah, x cross d tilde z. And finally, we will be in h1 d tilde z. This is the way the indices change. Okay. Well, now we have two lines. Let's compare them, right? So what can we say? Here we have identity, right? Here we will have maps in this way. So this one is induced by tau. No, what is it, tau or is it pi? Pi, I think I call it pi. This is pi upper star, right? Here we have pi lower star, and here we have tau lower star. Okay? Once you have a diagram, you want to know if it commutes. Indeed, it is the case. So everything here is quite easy. I mean, from not everything, but this left square and right square are easy just by functoriality. And something is going on in the middle. So in the middle, this commutes by projection formula that I will write right now, by projection formula. Okay, so let's see what should we prove. So start with the cycle alpha here. And just let me make a notation. It will be easier. So this one I will call beta. So that here I have p lower star of beta. Just because we assume that z1 tilde gives z1, right? Well, let's write what we want to have. So the projection formula tells you is that if you want to intersect here alpha times this one, then you may as well intersect these cycles here and then go down. So going down, you take p, the push forward, and then intersecting there, it will be p upper star of alpha times beta. Okay? So this is precisely the statement of the projection formula, and this gives you the commutativity of this diagram and the commutativity of the whole thing, which will lead to the conclusion. The action of Z1, so this map, which we still consider as a map between the third Betti cohomology for X. So what it does, it factorizes through the lower row, right? So it factorizes through this group, okay? Factorizes through H1 of D tilde Z. Okay, so why is it useful? Well, it is useful because we are actually interested to the action on the torsion here, right? And what happens, here, note, the group H1 D tilde Z has no torsion, never. Well, to see this, one can just use the exact sequence of sheaves, this one, and then just write down what it gives, and we see that there is no torsion in these groups. So these are very good news because we have this map is 0 on H3 XZ torsion. So we have this result for one component, okay. And we also have another component to consider here. And it's actually even easier, so maybe I'll just leave it as an exercise. Similarly, x cross x star equals 0. Actually, because H3 of little x with z equals to 0, which is kind of evident, put it in this way, right? Okay, so what we have, delta acts as identity, but because of this decomposition, it is also 0, right? It's 0 on H3 XZ torsion. So conclusion, the only one case when identity could be equal to 0 is when the group is 0. Okay, so this group is 0. And actually, it gives you just a sample of a general method, which was also used by Bloch and Srinivas in this case, just to use the decomposition of the diagonal and use the action of correspondences. And well, because of this kind of factorization, you may deduce all these results. Okay. So let me just make a remark. So remark is actually for x smooth, for x smooth, the same argument shows that if x has integral decomposition of the diagonal, Chow decomposition of the diagonal, this is actually what we've just used, right? Then you can also use the action of correspondences but on the Chow group of 0 cycles. And then it gives you that, that actually CH0 X is CR0 universally trivial. So this is a converse for lemma 1. That for a smooth variety, and smoothness is necessary to have the action of correspondences. So for smooth varieties, being CH0 universally trivial is equivalent to the fact that X variety has an integral decomposition of the diagonal. Okay. So now let me speak about some specialization properties of this notion. Well, I think that this is chapter 3, specialization properties. Okay, so let me first make a definition. So K field X, Y over K projective varieties. And F a map between X and Y. So we say that F is the definition. So is CH0 universally trivial if, well, the same property as for a variety, just a single variety over a field. So if for any field extension F over K. The push-forward map is an isomorphism universally between X and Y for 0 cycles. Okay. So this is a more general definition for a variety of wave-base. Now, when we have such a situation, you may wonder how to relate the property for X for the total space with the property of the fibers, right, as in the previous talk. So let me tell you the proposition. Everybody could see if I write here? Yeah, okay. So the second one. So in the situation of the definition, so xy over k, projective, and f from x to y is universally CR0 trivial if the following condition holds. CR0 trivial if it is the case for the fibers. But here, it's not only fibers at closed points, but really all the scheme fibers. Okay? So if for any m, so a scheme point of y, well, typically you will be interested in points coming from function fields of curves here. So for any m a scheme point of y, the variety x m, the fiber xm is CH0 trivial, universally, CH0 universally trivial. So let me just put it this way. So as a variety over the residue field, kappa of m of this point. Okay. So I decided to put this in as an exercise, and you can find it as an exercise in the list I put on my webpage if you want to know more. Okay. So now things about the specialization. Well, maybe just let me tell that we will apply actually this proposition for a desingularization of y. So here we will be actually interested in exceptional divisors of the resolution of singularities. So this will be typically a situation where we'll apply this proposition later. So now for the specialization, let me make following notations. So we take a discrete valuation ring, denote the big K field of fractions, and little k is the residue field. So the situation is the following. Consider a scheme over spec A, where this map is proper and flat. Well, then one is interested in the special fiber, which I will denote Y, over spec the residue field. And also the generic fiber X over the spectrum of the field of functions. Okay. In this situation, there is a so-called specialization map between the Chow groups of X and Y. So let me write it here. So in this context, so then there exists a map, there exists a specialization map. And it's actually very important for us, the existence of this map. Here. It's very important, and in this case, it's actually not complicated. So you can find the construction of the map in the book of Fulton in paragraph 2. So if you ever open the book, then you know that here there is not yet the whole complicated theory of intersection. So here what happens is just we view y as a divisor given just by a uniformizing parameter of the special fiber. So here actually it's not difficult to construct this map. And this one turns out to be fundamental for us. Let me give you a proposition. So proposition 3, so in this situation, assume A Hansilen. Well, it's a technical assumption which will be never necessary in what follows. X, the generic fiber here, the generic fiber geometrically integral. With a desingularization, so with a desingularization pi, x tilde to x, desingularization, so meaning that simply x tilde is smooth and proper. Okay, this map is birational, such that the degree map is an isomorphism for Chow groups of x tilde. So let me, for this proposition, just assume only this. Okay, then the conclusion is for 0 cycles on the special fiber. So then if I take psi, a 0 cycle in y of degree 0, and I assume that, that psi is supported on the smooth locus, supported on y smooth. So such a 0 cycle has a 0 class in y. Then psi equals to 0 in the Chow group of 0 cycles of y. Okay. So let me explain you the proof. So in order to prove this proposition, we will need the following classical lemma on moving of 0 cycles, which is, for 0 cycles, also not difficult to prove. Again, see list of exercises. So K field. So it's a moving lemma, so we take X smooth quasi-projective variety, and an open subset inside. So U in X, a dense open. So the conclusion is what you expect. Any 0 cycle can be moved to U. So if psi and z0 of x is a 0 cycle, then there exists xi prime, a zero cycle which is rationally equivalent to xi, such that xi prime is supported on U. So maybe if it's not clear, xi prime is still a zero cycle on X. Well, on X, so, but on U, well, depends how you see. So it is a zero cycle supported in U. Well, and in this case, it's especially in the case where K is infinite, but you actually do not need this assumption. But for infinite field, this is what I put in the exercises, and for finite field, it's more complicated, but it's still true. Okay. So now with this, we will be able to prove the proposition 3. Proof of proposition 3. So in proposition 3, we have our zero cycle here. Okay, xi is a zero cycle, which is given by the assumptions of the proposition. So take it. So so xi in what? In the zero of a y. Supported on y in the smooth locus. Now, because we assume that the ring was Henselian, just lifting each closed point which appears in the decomposition of xi, we can lift xi to the generic fiber. Because A is Henselian, implies that xi lifts to xi1, which is where? Which is on C0, in Z0 of X, but even we can say more, supported on X smooth, because we took xi also supported in the smooth locus of y. Okay, and now we will use lemma 3. So let's just assume that U in X smooth and open, such that the resolution of singularities induces an isomorphism over U. This exists just by the definition of what pi is. And now this cycle xi1 by lemma 3, we can move it to U, because here we deal with smooth quasi-projective varieties. Okay? Okay, maybe I write it here. So lemma 3 implies that there exists xi 2 supported on U such that xi1 and xi2 are rationally equivalent in the Chow group of X smooth. Okay, so now we can view xi2 as a cycle on Z0 of U, but also on X tilde, right? Because we assume that U was an open such that the resolution of singularity is an isomorphism. So we made this construction in this way that we could actually really see xi2 as a cycle on X tilde. Now what are the assumptions? The assumption is the Chow group of zero cycles of degree 0 here is trivial. This is the case for our cycle xi2, because the original was also of degree 0, right? So by assumption, xi2 equals to 0. in Chow groups, the Chow group of X tilde. Then, applying P lower star, we conclude that C1 also 0 in CH0 of X, because it's exactly the cycle which is rational equivalent to Xi2 once we consider them on X. And now we have our nice map, the specialization map, which is actually constructed in the natural way. So in the way that we get the original cycle. By construction of the specialization map. The image of Xi1 is Xi. So Xi equals to 0 in CH0 of Y. Well, maybe I should draw a picture just for this specialization map. Okay, so this is X, this is a generic fiber, and the special fiber, well, not necessarily reducible in general. So what are you doing with this lifting and specialization? If you take a point here, then you can just lift it to to a point which gives the original one by reducing modulo the uniformizing parameter, more or less. And similarly, if you have the point here, then you just extend it for the over the so this is X tilde, and this is over spec A. So if you have a closed point here, because X tilde is proper, then you can extend it for an A point. So here is an A point, and here is your specialization. So, and this is precisely the construction of the specialization map, which is exactly the inverse of the lifting, but that you can do. Okay, so, okay, so this is the end of the proof of the proposition 3. Well, now let me show you why is actually it is useful and why I actually gave you the proof. Okay, so it will be proposition 4, which now will deal with the universal CH0 triviality. So again, a discrete Fallatian ring, K a fraction field, and a little k a residue field. I do not assume anymore that K is Hanselian, just a discrete Fallatian ring. Now consider X over A, over spec A, flat, well, let me put it this way, faithfully flat. I want this map be surjective, faithfully flat, so just flat and surjective, and projective. And this time, I will assume that the fibers are irreducible. The two, the generic one and the special one. So both fibers are irreducible with geometrically irreducible fibers. Integral. Okay, I don't want a non-reduced neither. Geometrically integral fibers. Okay, now let me make a picture or a diagram. So here is the situation. We have X over spec A, our map. Here we have Y, the special fiber. And we have the generic fiber here. So now I will do some assumptions. Okay, so we assume that there exists resolution of singularities in both cases. Well, I didn't tell you that the field of characteristic 0 or something. I just assumed that there are resolution of singularities. Very often, the generic fiber will be already smooth. But still, they exist here, resolution of singularities. X tilde, and here as well, C over Y, resolution of singularities F. Okay, now the conclusion is that a universally CH0 trivial variety will be specialized to a universally CH0 trivial under assumptions on this resolution of singularities. So assume that X tilde is universally CH0 trivial. And F is a universally CH0 trivial map. So this is an important assumption, and which is in practical the one which has to be checked. So when we will apply this proposition, we will have to do some work in order to understand the resolution of singularities and if this actually holds. Okay. So this, and also assume, because I didn't assume that the field was algebraically closed, and for Alexei, I will assume that we have a zero cycle of degree 1 and not only the rational point. So assume that Z has a zero cycle of degree 1, which I call little x. Little x. So then the conclusion is that Z is CH0, universally CH0 trivial. So this is our first property, which is over the field Kx itself. And let me also give you a second one, which follows actually from the first, which is a geometrical one. So if little k is algebraically closed, and if I suppose that the resolution of singularities X tilde extended to an algebraic closure of the fraction field here is universally CH0 trivial, then, and also I assume F again is universally CH0 trivial map. So then again, Z is universally CH0 trivial variety. So this will be, I guess, the last thing I will prove today. So, well, not the last thing I will say, but the last thing I will prove. So let me give you the proof. Which uses the previous proposition. So the proof of the first version. The second one you can do as an exercise. So, okay. The idea here is to change little k by the function field of y and apply the previous proposition, proposition 3. Well, how we do this? So take eta in y, the generic point. We can do this, right? Then what we have as a DVR for the proposition 3, the ring, the local ring of the whole X at this point, because we assume that the fibers were geometrically integral. This is actually a discrete valuation ring. Okay? Well, it's not Henselian, but it's not a big deal. We just take a completion. Okay? Take B, the completion. Okay, now it's the ring we will use. So what we have here as the properties. So the residue field of this ring is the field of functions of y by the definition. And let me put big F of the field of fractions. Okay? Well, now, sorry, I realized that I change the blackboard every time I put notations here, and I just go directly to the other side. So I have to do this better next time. And okay. So here what we have. We have X base change to B. This is over spec B. Now we have here our generic fiber over the field F, which is big, yeah, but still we have the resolution of singularities here, X tilde K F, and this X tilde has a CH0, the group of 0 cycles 0 because of the assumptions on X tilde. And also as a special fiber here, we have Y over this field, over its function field. Okay, and we have still have the resolution of singularities with this function field. This is just by the base change. Now what we have, by assumption, we have that the Chow group of 0 cycles of X tilde over this big field is isomorphic to Z via the degree map. And now we have our interest in 0 cycle in here. It is Y minus X. Eta minus X. Eta being the generic point of Y. Right? This one is a 0 cycle of degree 0. And we may assume supported on Y smooth. Okay, now the proposition 3 applies, right? The proposition 3 applies to this situation, which tells you that because of this property, this one is actually 0. Eta minus X is 0, viewed on Z. Because we may assume that, so little x by assumption was the 0 cycle of degree 1 on Z, and the generic point of y, because y is geometrically integral, gives you also generic point of z. So these are very good news because it precisely tells you by what we saw last time that when the generic point is rationally equivalent, so it's 0, viewed on, maybe I have to write like this in the child group here. So if we have this equality, then it precisely tells you that here we have diagonal decomposition and here the universal triviality of the child group. Okay, this is it. Okay. Well, now let me give you a couple of other results also related with the specialization of the universal CR dual triviality. And the next time we will see how to apply these results for the questions of the stable rationality. Okay. A slightly different version of the previous one, but just we do not assume that the special fiber is irreducible. So this one is due to Totara. So the proposition, which is in this form due to Totara, is that as before, we take A, big K, and a little k algebraically closed. And then we are in the situation where we have this x over spec A, say projective faithfully flat. We have the special fiber and the generic fiber. And we assume that the resolution of singularities, that if there exists x tilde to x a resolution with, again, so trivial over k bar is CH0 universally trivial, then so nothing about resolution of singularities on y, but the conclusion will be about cycles supported on the smooth locus of y. Then, for any field extension of little k, and for any cycle psi in the group of 0 cycles on F of degree 0, and supported on the smooth locus of y, on yf smooth. So for any such data, we have psi equals to 0 in the child group of yf. Okay, so similar conclusion, but for cycles supported on the smooth locus. Okay. Well, now I will give you a global version of a specialization argument. You can see this like as a local version because we are over like DVR. So what happens if we are over a base? So here is the proposition. Okay, so proposition 6. Well, let me put it like this, due to Clairvoisin. Well, take K an algebraically closed field of characteristic 0. then consider a family. So family will be this time over a base, which will be just integral of finite type over K. B integral of finite type over K. And then we have a family X over B, with X are also assumed integral, and the map is dominant and projective. So sorry, this is a map, it's dominant and projective. Now assume that the following accident happens, that accidentally we were able to prove that for some point of B, the fiber has no decomposition of diagonal. So assume there exists just one point B0 in B, such that the fiber X over B0 has no integral Chow decomposition of the diagonal. Then the conclusion is actually that it was not an accident, but it happens very often. Then, for B, a point in B, which we have to choose very general. I will make it more precise. Very general. We have the same conclusion. The fiber X B has no integral Chow decomposition of diagonal. Okay, so just let me tell you what very general means. Characteristic 0. No, just no. Not for the resolution of the fiber, just for the fiber itself. So remark. So what does this mean? A very general point. So B in the K, very little k, very general, means that we were able to find a countable union of closed subvarieties of B. So closed, a countable union. And we take B outside this union. So we have to throw the countable number of conditions. Okay? So it's natural numbers. Okay. Well, to prove this proposition roughly, very roughly, the idea is to view the decomposition of the diagonal as an equation. So there is equality, right? Diagonal equals to something. But this equation, you view it using the Chow and Hilbert varieties. So you view this as an equation on these parameterizing schemes. Then the schemes have a countable number of components. Here, that's why we have a countable union here. But it's actually quite annoying to write it down properly to have all these closed conditions here. And the last proposition in this direction, which is personally I find very surprising, so due to Charvial and Totaro. Forget about the decomposition of diagonal and zero cycles, just consider family. So what happens here? So you take a sufficiently big algebraically closed field, so a universal domain. So thanks to Olivier, I learned that it means algebraically closed and of infinite transcendental degree. And infinite transcendental degree. And we take a map between varieties. So just, I don't assume a map between just integral varieties, so finite type, over omega. Then something very, very real happens. Then for a very general point on a base, for any I, the Chow group of the fiber is isomorphic, well, to the Chow group of the geometric generic fiber. The geometric generic fiber. So it actually tells you that if you want to prove something about the very general point, the only thing you have to consider is the geometric generic fiber. And the reason is that actually their x eta and the fiber for a very general point are isomorphic as schemes, as abstract schemes, not as varieties, but are isomorphic as abstract schemes. So that's all I wanted to say about specialization. Thank you. And so applications for tomorrow.